Okay, so we have just had a lot of lovely presentations on very many different models of computation, most of which, although there is one exception I've written down on this board here. So now I want to just give a little bit of a quick summarizing lecture and tell you what the Church-Turing thesis is, which is an important central thesis in computability theory. It actually came into a lecture on lambda calculus, but in any case, the main topic of this hour is going to be the Church-Turing thesis. So here we have lots of models of computation, not written in exactly the same order that they were presented today. I've written them in this order for a particular reason. And I want to just go a little bit through the history. So, as we said at the beginning of the course, somehow the motivation for Turing in defining the Turing machines was to be able to come up with a general notion, mathematical notion of algorithm, of what an algorithm is, of a mathematical model of essentially what we can state algorithmically, what we can formulate, what problems we can formulate algorithmically. And I'm going to start with the partial recursive functions and go down from there, because these are the various models that people have come up with, not all of them, but a lot of them, enough for us to talk about, where people have tried to formulate, give a general notion of algorithm. And the first successful one is the partial recursive functions, which, as I think I've already said, goes back to the early 1930s, and that basically worked by Gödel and Jacques Laurent. The early 1930s. Although they knew that they had captured a collection of functions that could be definable by algorithms. They didn't know that, they didn't propose that that was everything definable by algorithms. Church, who defined the lambda calculus, he was less modest in the sense. I'm not saying he was immodest, but he was, he did definitely propose, he was right to do so because he was correct. But when he proposed his model, he said, I think this captures all computable functions in 1936. And as we know, Turing's motivation was very much the same, and he also gave arguments for why his models, his Turing machines, plausibly do capture all algorithms that we can informally describe. So this was all at the same time. So all this happened in the 1930s. That was obviously intellectually a very exciting time to be alive. Computability theory, the results in logic of Gödel were all being developed at that time. Quantum mechanics was being developed at that time. Real sort of different way of thinking about physics. Of course, at the same time, it was a very troubling time for the world, because people in Germany in the early 30s had, through democratic processes, elected a government that did not respect democratic ideals. And that led to, as we know, all sorts of problems for the world. So I always think, looking back on this period, that it was a very exciting time intellectually, but obviously, in retrospect, a very troubling time, and one wonders how people are going to look back on the present period of time. Anyway, so of Turing machines, not long after that, Post came up with first of the string rewriting systems. We had a lot of string rewriting systems in all the different kinds so this was 1940s, I think, in the presentation on string rewriting systems. Also in the presentation on string rewriting, there was the notion of computability via grammars, which goes to Chomsky. It's due to Chomsky in the 1950s. The state register counter machines kind of came into vogue in the 1960s. There are lots of people involved, but especially I think Marvin Minsky in the 1960s. Cellular automata. That's very lovely models where you have like the game of life. I don't know when those originated, but a lot of work was done. That's the nice presentation on that said in the 1970s. So there are other people involved, but it includes Conway. And then we have variants on Turing machines, like adding non-determinism or probability, which is sort of similar because in both cases you're making a choice about what to do next. But in one case you're relying on some angel to tell you what to do, which isn't very realistic, whereas in the other case you're tossing a coin, which is something that one can more realistically do in practice. But anyway, these were developed in the 1960s and 70s. And then we've got the presentation, which we didn't have, but nicely it was put into the little part of it was put into the non-deterministic Turing machines. So there's also a notion of quantum Turing machine, which is an abstract model of computation where the physics underlying the model is quantum physics rather than just the classical physics that underlines our normal mechanical or electronic or whatever models of computation. So these were first proposed by David Deutsch, whose name I'm just trying to remember how to spell. It's SCH in the 1985. And there are lots of, that's a very powerful model based on quantum mechanics, but there are more less powerful variants which are also very interesting. So there's particularly something called quantum circuits. Then we've got hypercomputation at the end that people were talking about in the last. So this was sort of became, but it goes back. It goes back to Turing, as we saw with oracles. So that's so maybe I should put that was the late 1930s. But it became into vogue as a subject in the 2000s. So that's the 1930s to 2000s. The noughties, as we call them, the decade started with the naught, meaning zero. Well, and then we have real-world computers, which have kind of been available since the 1940s. That's the 1940s onwards. And of course, we should really draw a line here because up to this point, we're talking about mathematical models. Here we have something we actually work with, some devices we have that are engineered in the real world. So at the top there, I put automata. They came later. These are more restrictive models of computation, but they're studied because they model, they're useful in practice, as the talks showed. So there are innumerable kinds of automata. Finite and pushdown are just two. We've got the sort of most basic kinds of automata. There are many, well, we've also got the cellular automata somewhere down here. But anyway, there are many, many different kinds of automata. But the point is sometimes it's useful to look at restrictive models of computation to be able to model certain real-world scenarios. And in these, we're not trying to simulate. We're not trying to model the notion of what can be described by a general algorithm. So we're not trying to model general computation here. We're trying to model some specific aspect of computation. And as we saw in the presentations, all these models here, all the way down, we didn't have a full presentation on quantum Turing machines, but they're included. These models are all equivalent. Regard to what they define as being computable. If you use any of these models to define what it means to be a decidable language or a computable function on the natural numbers, you will get the same answer. So it's equivalent with regard to computability. Importantly, with computability there, as was nicely discussed especially in the presentations on non-deterministic and probabilistic Turing machines, importantly there, when ignoring efficiency issues. If one brings in efficiency issues, then it becomes, well, just all the equivalences become very much more subtle. Then one can take one normal way of dealing with it is efficiency up to a polynomial factor. So if there's a polynomial factor by which you equate things, that leads to big classes like polynomial time. If one has efficiency modulo a polynomial factor, then all the initial models are equivalent, but then there are still the tricky open questions regarding non-determinism and quantum computation. But anyway, in this course, we're not too concerned with efficiency, so these are equivalent with regard to computability, so ignoring efficiency. And part of all these models being equivalent, one way of showing that is every one of these models can simulate a Turing machine. So we saw that in some cases, people were showing that you can define every partial computable function, but we've seen that in the lectures that partial computable functions can simulate Turing machines, so therefore simulate a Turing machine. In other cases, we explicitly saw that these models could simulate Turing machines. That was particularly nice with the cellular automata with these big pictures of how that was going to work. Anyway, in the presentations, a number of people referred to Turing completeness. And what does Turing completeness mean? Well, a model is Turing complete if it can simulate any Turing machine. So a model of computation, let's go to the other board. It's Turing complete. If it can simulate any Turing machine. Well, that's a bit of an informal definition, because what does it mean to simulate a Turing machine? Well, you'll need to give a different definition of that for every model in question. And actually, in some cases, that's quite tricky. So I think it was the cellular automata, or one of the presentations was mentioning this result by, well, maybe it was a different one, by Matthew Cook on whatever rule number it is, from Wolfram's rules for cellular automata, or 110? Sorry, rule 110, yes. So I seem to remember there was, when that was shown to be Turing complete, there was some controversy about whether that, whether it really is Turing complete and what Turing complete means in that case. So it's not always straightforward. I mean, that's kind of what I remember. This was like about 20 years ago or something. So, anyway, So it's not always very easy to define for a specific model what it means to be Turing complete. But the examples we saw, it was clear they were Turing complete because we saw quite straightforward ways. Well, actually, with the cellular automaton, it wasn't straightforward, but anyway, one could see how a Turing machine was being simulated there. So we have this notion of Turing completeness, which actually isn't in the notes for today. It should be. I might try to put it in, but it was mentioned a few times, so I thought I should define it. Now the stubborn camera doesn't want to move. Oh, maybe because I'm pointing it the wrong way. So which of these models are Turing complete? These ones. All these models can simulate Turing machines. In the hypercomputation case, most of the models considered were Turing machines, but with some extra features added. So yeah, they cannot clearly simulate an ordinary Turing machine. You just don't use the additional features. So I missed that. The model I missed out from the presentations was partial combinatory algebras. If one's going to put that in, I might put PCAs here, because a partial combinatory algebra in general can simulate a Turing machine, any partial combinatory algebra, apart from the trivial one that has K equals S, that one can't simulate a Turing machine, but other partial combinatory algebras, they can all simulate Turing machines, but only in special cases are they equivalent. So of the ones that were presented, the K1 and the lambda calculus are equivalent. But Kleener's second model, there's a computable version and a non-computable version, and the non-computable version is not equivalent. So PCAs, I see them as a sort of slightly different beast in a sense, in that it's a nice algebraic formulation of an abstract structure that gives you the kind of things that a model of computability gives you in a general setting. So you can apply functions and program by recursion and so on, but you don't necessarily have that everything can be described by an algorithm. It might be a more powerful setting than that. Anyway, so these are Turing complete. So why is the green box so important? I mean, you know, hypercomputation and the funny, powerful PCAs, you know, these are great things in theory, because we can decide the halting problem with several of the models of hypercomputation. Wouldn't that be fantastic? The problem is, how do you actually build one of these hypercomputers? It would be very difficult, although maybe what I like about the model that I mentioned at the end of the presentation with the closed loop in space-time is there is at least a plausible, well, not very plausible, but there is at least a physical story behind how one would implement that. So being Turing complete is an important property. We can describe any algorithm, we can formulate any Turing machine. Another important property, which was again mentioned in a few talks, is being, one might say, physically realizable or physically feasible. Let's use realizable, which means the model of computation is such that we can realize it by a physical device. And it is really pretty reasonable to say that all the models up from this point, so this is from quantum t ends up, are physically how is it spelled physically? Realizable. Now you might say, with a Turing machine, how can it's physically realizable? We need an infinite amount of paper tape to realize a Turing machine. But it's physically realizable in the sense that you only need a finite amount of paper at any one time. And if you're going to run out of paper, you just go down and cut another tree. And if you run out of space on planet Earth, you go and find another planet that has trees on it and get some paper from that or something like that. Anyway, I mean, there's a kind of clear sense in which it's reasonable to describe these as physically realizable.
The real world computer is from.
Right, and so the other model that is, so this is different because it's not a mathematical model, but this is not just physically realizable, this is physically realized. So this is, we should have this, so this is physically realized. Oops, sorry, I'm not writing very neatly, but there we go. In the case of hypercomputation, you know, it's things like closed time-like loops or accelerating in a sort of Zeno-paradox way that every step takes half the time of the previous time. You know, this is kind of physically realizable in science fiction books, maybe, but so you could say that's kind of science fiction, but this is physically realizable in the real world. I mean, there's kind of a question mark here with quantum Turing machines, because as you may know, there are these powerful algorithms for quantum computers, like this most famous one is Shor's algorithm that factorizes composite numbers into their prime factors in polynomial time. But it's a major research area to actually try and build quantum computers that can perform quantum computation. So we've got a bit of a question mark over the physical reliability of quantum Turing machines. It doesn't matter that much because in any case, it's not going to give us any new power in terms of computability. So we have this observation that our box of equivalent models is exactly those models that are both physically realizable and can simulate a Turing computer. And Turing's thesis is kind of that that's not a coincidence. So Turing's thesis, well, the Church-Turing thesis. It used to be called, I think Pliny first called it Turing's thesis, but it was sort of, I know, Pliny first called it Church's thesis, because Church was the first one to say, my model includes all, my model defines all computable functions, but people started calling it the Church-Turing thesis because Turing's work was done independently, and Turing is the one who gives a plausible argument for why his model covers all the really models the notion of algorithm. So we're going to have two versions of it. So again, this is not quite in this way in the notes. If I'm going to rewrite the notes, I would prefer to write it in this way. I'm not sure I'm going to have time, but the way I would do it now. So we're going to have two versions of the Church-Turing thesis. Version 1. And this says that whenever we have a physically realizable model of computation that is Turing complete, it is equivalent to a Turing machine. So that is, we can't go beyond the power, once we've got the power of a Turing machine, we can't properly extend it in any way within the realms of what's physically feasible. So, so version 1 of Turing's thesis, any model of computation that is Turing complete and physically feasible is equivalent to TX, Turing machine. But there's another way of saying this, which It's a bit less precise, perhaps, but I think captures the flavour of the idea just as well, if not better. We've got CT thesis version 2, and that is, we can't. So if we were trying to informally define what an algorithm is, certainly what Turing machines can do is algorithmic. So we would certainly want to be able to simulate a Turing machine because that is an algorithmic process. And we want our algorithms to be physically realizable in the real world. So we want these two conditions to be satisfied by algorithms. And version 1 says we can't go beyond that. So one could say that the Church-Turing thesis says that the Turing machine notion of algorithm is equivalent to the informal notion of algorithm. If you have whatever model we're going to have for our informal notion of algorithm, because it needs to be physically feasible or realizable, and obviously needs to simulate a Turing machine because that's clearly an algorithmic thing, we're going to get something equivalent to a Turing machine. So the informal, so the version 2 is the informal notion of algorithm is equivalent to TM, to the TM model, or to any of the other equivalent models. What I like about this last version is, I mean, my way of looking at this, you ask, what does it mean to have an algorithm? It's a sort of philosophical question, at least it would have been considered a philosophical question in the 19th century. So this is this thesis is saying, we've got a philosophical question, what is an algorithm? To which we have a precise mathematical answer, Turing machines or any equivalent model. And it's very rare that a philosophical question can be given a precise mathematical answer. Now, there's a question whether this answer is correct and how rigorous the thesis is, because obviously the informal notion of algorithm is informal, so in some sense you can't make it more precise. But still, it's a philosophical question. We're proposing a mathematical answer to it, the Turing machine model. And it's widely accepted because there is no other competitor as an answer. So people have tried to, in all different ways, to find different models of computation that might give different answers, and they're all, once they're physically realizable and Turing complete, they're all equivalent to the Turing machine model. Okay, so I want to finish in just 10 minutes' time, so I just want to speak about, well, make 2 points to do with the Church-Turing thesis, and maybe I'll use the so before I rub off the models, are there any questions about this sort of list of models? Or... No. Yes. No. About philosophical questions having mathematical answers, I'm not sure I can think of it. I mean, you might argue that maybe it's not really a philosophical question, but anyway, ignoring that, I can't really think of any other example of a philosophical question that has a precise mathematical answer which is widely accepted. Be interested if you have other good examples of similar phenomenon. It could be logic, or logic, example logic. Yeah, let's discuss this at the end, because it's a nice thing to discuss. But I do want to finish with the lecture. So the 2 points I want to make about the Church-Turing thesis, so it's widely accepted, and in fact, we kind of make use of it because it's widely accepted, and we use it in two different ways. And this is, and both things are important. So we use the CT thesis in two different ways. Oh, that's not a good pen. Let's divide the board. So one is sort of positive way, and that's when we want to show something's computable. And we have a definition of computable, so computable by a Turing machine, or take any of the equivalent definitions. We have a whole lot of equivalent definitions. We want to show something is computable. If you use any particular model of computation, it's very often very tedious to show it's computable. So defining, we've not been defining an actual Turing machine for a long time now. We only did that in the first week, and we used high-level arguments that Turing machines exist. It's obviously very tedious to provide actual Turing machines or actual proofs that things are partial recursive functions and so on. So if we accept the Church-Turing thesis, to show something is computable, all we need to do is give an informal algorithm. And as long as that algorithm, as long as we can see it is an algorithm that we can follow in the real world, so it's physically realizable with precise steps in time, then by the Church-Turing thesis, it must be encodable on the Turing machine. So we use the Church-Turing, so we give an informal algorithm and invoke the Church-Turing thesis to conclude it is TM computable or partial recursive or whatever. Okay. So that's very useful. But the question is, if you do this, have you really given a proof? Because we've proved something's computable by giving an algorithm, an informal algorithm, and then invoking a widely accepted philosophical thesis, but that's something that we can't, that thesis is itself, something one can't prove. But actually, this is okay, because this, in practice, because this is an inessential use. An essential, that's a double S, in essential use of the CT thesis, in the sense that we're really just being lazy. Because what we could do, we have enough experience when we have an informal algorithm, we've done weeks of converting stuff to Turing machines to greater or lesser degree. What we could do is, roll up our sleeves and actually get to work and define we could always actually put the extra work in and define the Turing machine. Because we could actually do the work, define a TM, that does the job. If you ever get to a situation like this, in which you can't define a Turing machine that does the job, but you have a precise physically realizable algorithm that that you have that has precise steps that can be carried out in time, then wow, you've discovered a new algorithmic process, and that would be an absolutely earth-shattering thing. So, you should then find out what is in your algorithm that can't be put into a Turing machine, and extend the Turing machine model and extend the notion of computability. But actually, in practice, it's an inessential use because we know that if we put in the extra work, and it's not even that difficult, it's just very tedious, we would be able to define the Turing machine. Okay, so the second use of the Church-Turing thesis is when we show that something is not computable. E.g., Hilbert's 10th problem, which was the whether or not a Diophantine equation has a solution. I mentioned this in the first lecture. E.g., the proof is Hilbert's 10th problem. It's not computable according to does not have a computable solution is not decidable according to the Turing machine definition of decidability. If you told this to Hilbert, then he might say, so what? Why should I care about the Turing machine definition of decidability? But proofs of undecidability, like this, become really important. They gain much more importance due to the Church-Turing thesis, because if you accept the Church-Turing thesis, then when you have a proof of undecidability, which to give a proof, it's necessarily with respect to a model, it becomes an absolute, a proof of absolute undecidability. You will never, by any means, find a physically realizable algorithmic process that will decide the problem. So using the Church-Turing thesis, we're here using the CT thesis, we conclude it is undecidable by any physically realizable notion of algorithm. And I would say this is an essential use of the Church-Turing thesis because we only get this conclusion by virtue of accepting the Church-Turing thesis. So this is essential. Okay, anyway, it's up to you whether or not to choose to believe the Church-Turing thesis, but from now on, we will believe it. I mean, I will believe it. I already do. But we will be using it in this course quite often in this way, but whenever we prove an undecidability result, the result is interesting because of more interesting than it would be otherwise because of the Church-Turing thesis. Okay, so that's the lecture today. Are there any questions? Well, I think you don't practically use the thesis. I mean, we prove undecidability with respect to a model, but that undecidability has a greater meaning because we believe the Church-Turing thesis.
Undecidability with respect to the model.
Well,
You mean you show that it's not decidable with the
yeah, for example, yes.
Yes.
Yes, sorry, that's what I mean. Yeah, that's right.
Yeah.
Yeah. Okay, good. Other questions? Right, well, I shall stop the video then.